start. Please welcome Peter, our next speaker. Take it away.
Okay, thank you, Stephen. It's great to be with you today. I'm Peter Lindes. I'm a PhD candidate in the Soar lab working with John Laird, University of Michigan. And I've been working on the language comprehension system that we need in order to do interactive task learning. You've heard a lot about interactive task learning already today. And now this is getting into how within SOAR we can comprehend the sentences that come in during that instruction. So I'd like to start by saying, what is the real research question we're trying to answer here? And actually, I think there are two questions. One of the things I'm most interested in is learning, how do humans comprehend language? And then a second question is, how can we make AI systems that comprehend language to be able to communicate with humans? And I think it's reasonable to say that maybe if we understand better human comprehension, that can help us build better AI comprehension systems. Because to communicate with humans, if we understand what humans are doing, that should help. And if we can build models of this human comprehension, that can maybe help us understand better what's going on in humans. So to turn all that into a more specific question that we want to work with, we need to figure out what is the process that could do a couple of, or three things, these three things. Construct actionable meanings from sentences, do that in real time, and use mechanisms that are similar to those in the human mind and the human brain. Now, one clarification here, you can talk about language understanding at several different levels. There's the speech recognition level that just takes sound and turns it into a sequence of words. And there's the interactive task learning where we use the results of sentence comprehension to reason about what's going on in the world and learn tasks. At the middle of the sandwich is sentence comprehension, which goes from a sequence of words to an actionable meaning that the agent can act on. And that's going to be what our main focus is today. So what's human-like comprehension actually like? Well, first of all, it's functionality. Humans can do what I'm calling end-to-end comprehension, which means take a sentence in on one side, and on the other side you have a representation of its meaning that the agent can actually act on and do things with. And this has to happen in real time so that we can have live interactions. It has to be very general because we can put words and syntactic structures together in all sorts of novel ways that we've never heard before. And humans also acquire this knowledge of language through experience. Also, there are psychological experiments that tell us a lot about processing. Humans do something that's called immediate interpretation, which means when we see the meaning of a word or a phrase, we right away, we don't wait around till we get to the end of the sentence, we right away ground that incremental piece of meaning to our perception or our imagination or knowledge that we have. And also, natural language has a lot of ambiguity. So a key part of human language comprehension is resolving that ambiguity. Humans also predict what word is going to come next. What's the most likely thing to come next? And there's also a lot of empirical research on details of timing of human comprehension. And another thing is all this comprehension in humans goes on in the human mind. So it has to use human cognitive abilities, which may include long and short-term memories, some kind of dynamic selection of what kind of operations to do next, and various sorts of limitations on both timing and memory capacities. So these are the kinds of things we want to model in an AI system. And there are a couple of important principles that come out of this. First of all is compositionality, or that the meaning of a sentence is composed from a lot of small pieces, where each piece takes a piece of linguistic form, which might be a word or a way that 2 or 3 words are combined into a larger structure, and figures out what is the meaning of that small piece, and then composes these pieces into bigger and bigger pieces until we get the meaning of the whole sentence. Another is incrementality. There's a lot of psychological research about processing one word at a time, and something that we're adding that I haven't seen in the psychological literature is one construction at a time, where a construction is one of these small pieces of mapping form to meaning. And we're going to talk about that more as we go on. Another important principle of processing is selection. But often we have multiple possibilities, and there's processing going on in parallel, looking at all these possibilities, which we see as a fundamental thing going on in Soar. But then in Soar, a particular operator gets selected, or in language processing, a particular possible construction gets selected for further processing. So historically, Alan Newell got started on ideas about how Soar might do language processing. And there was a system called NL Soar that was developed by Rick Lewis and other people at CMU in the early 90s. More recently, Darrell Lonsdale at BYU and some other people worked on something called XNL Soar in the 2000s. And then about 2013, John Laird, on his sabbatical, spent a lot of work on building a parser in Soar that's been the workhorse for language comprehension for building Rosie and the things that Aaron Mininger and James Kirk talked about. And then since I came in 2014, I've been working on this new system called Lucia, which also works in the Rosie environment, but it has a more general model of how to process language, which we're going to talk about. So how does this Lucia Comprehension work? Well, first of all, the goal is to get the meaning of the sentence. So suppose we have this sentence: pick up the green sphere. What we want to end up with when we're done is this message to the rest of Rosie that says, do this operation, which involves this action you already know about, a pickup, and on this object. And these are just internal identifiers inside Rosie that it can use to identify both the action and the object. So how do we do, what goes in between there? Well, here's a lot of information about how we make that process of end-to-end comprehension work. First, we're doing it with incremental processing. All the numbered items you see there are instances of constructions that have been built in the order of the numbers. So we get pick and up, and we combine that into pick up, and then we immediately ground it to the agent's memory of the pickup action. And then the green sphere, green gets grounded to what we know about colors in the visual system. Sphere gets grounded to what we know about shapes. And then we put that together in number 7, the referring expression, that gets grounded to the green sphere that's in our perception. And now that we have both the object and the action, we can put them together into this number 8 transitive command that then gets formatted into a message that turns to Rosie. So here we see both end-to-end comprehension, we see incremental, or I'm sorry, immediate interpretation in the green arrows, and we also see, well, we don't see too clearly here, but we're going to see more about how this is incrementally done in Soar. So the whole process involves, for each sentence, we have, let's say the instructor gives us an input sentence. That goes into our processing algorithm, which also has access to a bunch of linguistic knowledge that's in Soar long-term memories. It also has access to this shared agent knowledge to ground things to, produces an output message that goes to the operational part of Rosie that then can interact with the world and also produce a response back to the instructor. And we go around this loop doing interactive task learning. So what goes on more in that processing algorithm? Well, here's kind of a flow chart where we start a sentence coming in, and the end result is to get this output message. So we're going to go around a loop here where we're processing one word at a time. And then at the next lower level, we're going to process one construction at a time. And so there's a word cycle and a construction cycle. The construction cycle has 3 main parts. We first have to select what construction to do next. Then if we found one, we go on. If not, then we're finished processing that word and we go get the next word. But if we have another construction to add, then we integrate that construction into the comprehension state and ground its meaning. And we keep going around that loop until there's no more to do with this word and we go on to the next So the really key contribution in the algorithm here is this idea of the construction cycle and those three phases of it, which are selection, integration, and grounding. Now we have this long-term knowledge. So over here in this upper right-hand corner, this represents the long-term knowledge that that algorithm is using. Well, where does that long-term knowledge of language come from? We're using a formalism called ECG, which stands for Embodied Construction Grammar, that was developed at UC Berkeley. And so we have a grammar written in this high-level grammar ECG language, and that's translated by a program into data that goes into Soar's long-term memories. And where does this grammar come from? Well, so far it's written by a human. And there's an incremental process where we have this big corpus of sentences we want Rosie to be able to understand, and we take one sentence at a time. So we take an input sentence, and we have these reference messages. So we pick an output message that we want that sentence to generate. We compare the two, and then this guy called developer, which happens to be me, takes that and puts new information into the grammar, and then it gets compiled by this translator program into Soar's long-term memory. So let's look at an example. This is one of James's puzzles, a simple blocks world puzzle, where the goal is to take this stack of blocks and reorder it into this stack of blocks. And here's the whole instructional dialogue that it takes to teach Rosie that task. And we're not going to go through the whole thing, but I'm going to look at a few particular sentences in here and some of the issues that are involved. So some of the challenges in trying to process all of James's 60 games and puzzles. So let's take this sentence. This is defining an action model that we've been hearing about today. You can move a clear block onto a clear object. So that's kind of a general principle that works in the blocks world kind of environment. But an important thing is that these referring expressions here are hypothetical, because we want this to be a rule that we can apply to all sorts of different things in the future. It's not just, we're not going to ground it to specific things in our current perception. So we have this hypothetical mode where instead of grounding to specific objects, we just output as part of the output message of the comprehender a description of the object that can then later on be used to decide what it goes to in the world in a real situation. Here's another sentence from that script. If a location is not below an object, then it is clear. But what does it refer to? It refers back to this location, which is part of the same sentence. So we need to be able to handle those kinds of back references. Here's another example. The goal from the same script. The goal is that a red block is on a green block and the red block is below an orange block. So this red block needs to be the same block as this red block. And when we process all this and we tell the agent, go ahead now and solve the puzzle, it actually does this. And notice we end up having a red block that's on a green block and it's below an orange block. So it understood all these things. Now let's look at a little more complicated example. This game's called King Stacked Frogs. And what you see here is 4 locations. Each one has one of these black tokens sitting on it. And one location is marked with red as a special location. And what we want to do is end up stacking all these tokens on the red location. But we can't just do it in any arbitrary way. There's a complicated rule that says how we can do this stacking. And here's the rule. If the number of the locations between a location and a covered location is the number of the blocks that are on the covered location, then you may move it onto the former location. So there's one thing on this location, and this is 1 square away, so we can move that. Now there are 2 things here. This is 2 squares away, we can move that, and then finally we can move it. So, but that's a complicated sentence even for a human to understand. So what kind of issues do we have to deal with? First of all, there are words that haven't been in our development set before, like number of and between and covered. So we need to make sure we add those things to the grammar. We also have several of these back references in this sentence. The covered location refers back to a covered location. It refers back to these blocks we're talking about. And this, at the end, the very end, the former location refers all the way back to this location. So this is kind of complicated. Here's a diagram of the final meaning structure that comes out of this. The green ellipses are meaning structures, and the blue rectangles are the pieces of language that went into creating those pieces of meaning. And so here we see that we have two things, a covered location and the covered location, that end up pointing both to object 8. And the blocks and it both point to object 10. So we've been resolving those co-reference situations. And finally, when we do all that and we run the agent, Rosie indeed stacks all the blocks up using that rule. So what have we accomplished? We've started out a couple of years ago with 50 sentences, and we got those working. We translated them to Spanish, and got those working. Then we had a baseline of over 200 sentences that was published in 2017. And now we're working on various ongoing experiments, spreading activation, which I'm going to talk about in my second talk, the 60 game scripts of James's that you heard about this morning and that I gave some examples from, and then these task learning scripts that Aaron is working on. So we're working on getting Lucia to cover all those things. So have we done human-like comprehension? Well, in terms of end-to-end, we've got around 300 sentences that are working in Rosie right now. We do that at a rate of about 138 words per minute, which is just a little bit slower than humans. We've done some few experiments with generality where we can take one form of a sentence and generate 1,000 more sentences that the system still recognizes. The acquisition still has a human in the loop. We do
Just let me know you have about 3 minutes.
Thank you, Stephen. It does ground things right away, as we saw some examples. I haven't talked about it in this talk, but we have many examples of how it resolves ambiguities and does local repair. We're not yet simulating the prediction and timing details. In terms of human cognitive abilities, it does use Soar. Right now, as I'm going to talk about in the next talk, all this linguistic knowledge is going into Soar's production memory. But that's something we're in the process of changing, and we're not yet simulating all these timing and capacity limits. So some nuggets are that it works for a lot of Rosie sentences. This embodied construction grammar has turned out to be a very powerful tool for doing this. And we've learned some things theoretically about this idea of the construction cycle, about how grammar works, how to have semantic precision. And some goal is that increasing the coverage is still a slow process. We need a good way to measure generality. We need this context sensitivity and some more comparisons to detailed human data. So that's all I have to say in this talk. Do we have any questions, Stephen?
Yeah, there's a question from the chat. In some systems, so Keith Lambert says that in some systems, like GPT-2 or 3, they seem to get semantics directly from syntax. Your approach seems to be that syntax is not enough. Could you help provide some, I don't know, enlightenment for that debate?
Well, there's probably a long answer to that question. I think those systems, I wouldn't say they get their semantics from syntax. They model words in context and build statistical models of word meanings and how they relate to each other, and then just process lots and lots of sentences. The big problem with that is when you're talking to a robot, you need not just a statistical answer. You need to know exactly for each individual sentence what the robot is supposed to do. So even if I know 90% of the time this is probably going to get a pretty good answer, that's not necessarily good enough for a lot of robotic applications. So this approach is using a symbolic approach, gives us much more semantic precision, as I was saying in one of my nuggets. There's a lot more that could be said about that.
Well, I don't see any more questions in the chat, but it looks like we have less than a minute. So,
Oh, I see one question here. Is real time actually simulated real time? Yes. When I say it's doing in real time, that's counting up the decision cycles in Soar and counting them each at 50 milliseconds.
all right. Well,